So we're looking at problem number 38 from chapter 19. We're given a rectangle that has a current running around it, and it is attached by these two axles that are non-conducting. It is placed into a B field, and we're given the magnitude of and the direction of the magnetic field and the magnitude of the current. We're told what the lengths of these sides are. We have A equals 0.12 meters and B equals 0.2 meters. And we're told that initially this is in the XY plane. So what that means is once we find our induced current, this rectangle is going to start to spin as it's placed in the B field, and then it's going to come out. It's either going to spin outwards or inwards into the Z direction. So we're asked to find the net force on the left and the right side of the wire segment. And we're also asked to find the net force on the top and bottom wire segments. And then after all that, we're asked to find the total net torque on the loop. Okay, so we want to make sure that we recall force on a current carrying wire. Magnetic force on a current carrying wire is going to be B times, so the magnetic field magnitude times the, what is that? Oh, I already wrote it down. Cut that out. So magnetic field magnitude times the current times the length times sine of the angle between the field and the current. Okay, so this is where we're supposed to be. Okay, so everything is still the same. I just don't have all of the work written out yet. So we have B times I times L times, and it's going to be sine 90 for this. For the angle between the B field direction, right, the B field vector, and then the current vector, because we're looking at the left and right wire segments. Okay, so let's plug everything in that we have. So that's going to equal 0.25 Tesla times, what was the 3 amps times the length of the segment, which is 0.2. Sine 90 is 1, and that gives us a value of 0.15 newtons as our magnitude. And so then we're going to look at this. Let's look at the direction by using the right-hand rule. So using the right-hand rule, we place the fingers of the right hand downwards in the Y direction, and then curl them towards the X direction. Then the thumb should be pointing straight out in what we call the positive Z direction. So for the left wire, we'll say the force on the left-hand side is equal to 0.15 newtons in the positive Z hat direction. Or other words, it's coming out of the page. We can assume that the force is going to be the opposite on the other side, but let's make sure it's definitely in the Z hat. So let's use our right hand rule. We point the fingers of the right hand straight up along this current, curl them to the right, curl them to the right following the B field, and then you're going to get a force pointing into the page, or the negative Z hat direction, just as we had expected. Great, so that's A and B. So now we want to go to parts C and D, where we're asked to find the force on the top and bottom segments. So for this one, we take the same stuff, but let's make sure our angle is correct. So here we want sine of the angle between the magnetic field vector and the current vector. Well, this one would be, for this bottom, it's 0 degrees. There's no angle between them, right? If we move this down, it's the same. They're parallel. Same thing here. This would be 180, right? But sine of 180 is 0. Sine of 0 is 0. So this is all going to be BIL sine 180 as well is 0. So on the top and bottom, so on the top wire and the bottom wire, we don't have any force. We only have force pushing on the sides. So what does that mean? Now that we need to find the net torque, torque is equal to B times I, and instead of L, it's area of the loop, sine of the angle, which we know is going to be 1, because we're talking about the B field that goes this direction and the current that either goes down and up or up and down. So this is fine, we can ignore that. So then we get 0.25 Tesla times 3 amps times point. So now here's the change, 0.12 meters times 0.2 meters. And this gives us a value of 0.018 Newton meters. And it's going to be spinning, since the force is coming out here and in here, so it's going to be spinning this way. That'd be counterclockwise if we look from the top. So I'm going to say counterclockwise from the top. One other way, real quick, that you could do this is if we recall that torque is equal to RF sine theta from intro mechanics, and then we would have the length, R would be the length of, R would just be the length of the side, and if you plug that in, you should get the same answer. Okay. So, cool. Not quite to that problem. We need to add a page here so that we have some room. Okay, so now we're looking at problem number 47. We're told that someone is walking around with a pacemaker, and it's working just fine. It has a sensitivity to 1.7 millitesla, right? I think that's what they said. I'm drawing this because of what we're being asked, which is, this is a current carrying wire carrying 20 amps, and there's going to be a B field around it. It's going to be going this way. Oop. This way. How close can this guy get to this wire that's carrying the current? Because if it's interacting with anything greater than 1.7 millitesla, the pacemaker might malfunction, right? That's the general idea. So what is the distance that this person can go in relation to the wire? So let's use B field for a current carrying wire. Mu naught, magnetic permeability of space, times the current over 2 pi times the distance between the current and the interaction, right? All we have to do is rearrange this. And plug in what we know. This is 4 pi times 10 to the negative 7 Tesla meters per amp times 20 amps. 1.7 times 10 to the negative 3 Tesla over 2 pi. This gives us a value of around 0.00235 or 2.4 millimeters. So if you're wearing a pacemaker, don't come within 2.4 millimeters of a 20 amp carrying wire, because you might have some problems. Good to know.